Hi, welcome to Unit 5.1. In this video, we're going to be discussing the first half of key question 1, which is how is chemical equilibrium quantified? So numbers there. And this video is divided into 3 parts. This is part 1. All right, so let's start off with what is chemical equilibrium. Chemical equilibrium exists when the rate of the forward reaction equals the rate of the reverse reaction. So before we get into that a little bit more, I just want to point out some equilibrium arrows that you may see, starting with reversible reaction and equilibrium reaction arrows. You've probably seen these before, and the main difference between a reversible reaction and an equilibrium arrow in terms of the way they look is that for the equilibrium reaction arrows, they're kind of like a partial arrow. Now, when you see an equilibrium reaction arrow, you know the reaction is at equilibrium, and that's when this should be utilized. But for the reversible reaction, it just means that both the forward and the reverse reactions are occurring or could occur. And so you don't know if the reaction is at equilibrium. These are kind of used interchangeably, so it's not a big deal if you sort of misuse them, but technically the way they should be used is that the equilibrium reaction arrow should only be used when the reaction is at equilibrium. Now, the next set is a little bit more important because these are the things that you really want to pick up on. So let's say, for example, you have a reaction that's at equilibrium or maybe even not at equilibrium. And let's say in that case, the forward reaction is more favored for whatever reason. So it's a more favorable reaction. The way that would be drawn is you would see the top arrow, which is going from reactants to products, longer than the bottom arrow, which is going from products to reactants, right? So basically the arrow for the forward reaction is going to be longer if the forward reaction is favored. On the flip side, if the reverse reaction is favored, that arrow going in reverse, so going from products to reactants, that bottom arrow is going to be longer. And that's something that's could be important, an important clue, or something that you want to pick up on when solving problems. So just to give you an idea of what you'll be seeing in this unit. Okay, so we're talking about equilibrium. Why is it important to learn this? You may recall from thermodynamics that most reactions tend toward equilibrium. So if you wanted to control a reaction, you want to know what are its equilibrium conditions? Like, what are the best conditions to get it to go to equilibrium? And as you also may recall from the thermodynamics unit, is that as a chemist, when a chemist is studying a chemical reaction, they want to know the two main things, kinetics and thermodynamics, where kinetics is the rate of the reaction and thermodynamics is basically the energy changes associated with the reaction. Equilibrium sort of ties these two ideas together. And so because equilibrium occurs when the rate of the reaction, so that's kinetics, is equal to the rate of the rate of forward equals the rate of the reverse, right? So that's the kinetics part. And then, so the concentrations of the reactants and products don't change, and that would occur when your system is in a stable state. And so that's the thermodynamics part. All right, another reason why it's important, aside from just chemists wanting to know it so that he can control reactions, is also because without equilibrium, you would actually die. So let's talk about 2 examples of when you could die without equilibrium. The first one being the blood buffer system. So basically, your blood has to maintain a very small range in terms of the pH. If it gets too high, meaning too basic, or if it gets too low, meaning too acidic, you could die. And so there's a buffer system in your bloodstream, which basically consists of chemicals that sort of maintains that pH. And the thing that makes a buffer system work is the fact that there's an equilibrium reaction between the acid and conjugate base or vice versa. The other example would be the sodium potassium levels in your cell. Once again, you have to maintain a balance of the right amount of sodium potassium levels. And so there are chemical reactions that also sort of help to maintain that. And those reactions are, again, driven by equilibrium. So these are just 2 examples in terms of in your body where equilibrium is important. So anyone thinking about studying biochemistry or studying any of these systems in terms of medicine, then you will realize that equilibrium is super important. Okay, so let's go back to the idea of equilibrium being a case where the rate of the forward and the rate of the reverse reaction are equivalent, meaning that the forward reaction is going just as fast as the reverse reaction. So let's say we have a plot here of, you notice that on the y-axis is rate and on the x-axis is time. When you start off a reaction, let's say you're starting off with your reactants, you have, at the start, you have the most reactants available. And so because you have so much of them, the rate of the reaction is going to be at its highest for that forward reaction. But then as you start using up the reactants, the rate will decrease. And you'll see more of this when you get to kinetics. On the flip side, at the start of the reaction, you have no products. And then slowly you start to gain some products. And as you gain products, the more products you gain, the faster the reverse reaction, the rate of that reverse reaction. So basically, as you can see from this chart, the rate of the forward reaction will decrease and the rate of the reverse reaction will increase until you get to equilibrium where they are at an equal rate. Okay, so at equilibrium, rate of forward equals the rate of the reverse, but it's important to know that that does not mean the reactions stop. It doesn't mean the forward reaction stops or the reverse reaction stops. They're still going, it's just that they're going at equal rates. Another way of looking at it is, let's say you plotted the amount of reactants and products versus the time. And so again, we said at the initial, you're going to have a lot of reactants and no products. And so what's going to happen is the amount of reactants are going to decrease over time and the amount of products are going to increase over time until you establish equilibrium. And this portion here is where the equilibrium will occur. You see where they sort of, both lines will flatten out. So notice that the amount of reactants and products stop changing. They're no longer increasing or decreasing. And so just to summarize, and this is what you're going to write in on your handout. So before the reaction, the amount of reactant will decrease. You want to write decrease here. And the amount of product will increase. That's before equilibrium. And then once you reach equilibrium, the change in reactant and product will stay the same. That does not mean that the concentration of reactants is equal to the concentration of products. It just means that they're not changing anymore. And you can see that in the graph, that the concentration of the products is different from that of the reactants, right? The amounts are different. However, there's no longer a change. Okay, so this is what you should have written in the blanks there. Sorry, I didn't have that up before. All right. Now, these two graphs could both be on the AP test because they like to test your plot reading skills. So it's important to sort of make sure you pay attention to what's on the y-axis when you're looking at the graphs, whether it's rate or it's amount that they're plotting. And the other thing that's important is to be able to figure out where equilibrium is occurring, what time is equilibrium occurring. So in the case where it's the rate, it's going to occur where the two lines sort of merge because the rates become equal for the forward and the reverse. And when it's the amount, it's going to be where the two curves sort of flatline because they're no longer changing. And so that's the time where it would reach equilibrium. So again, you just need to be able to read these graphs. Okay, so we're going to continue on in part 2 in a moment. But before we do, I just kind of want to go over this graph that we'll be using in part 2 because it ties into what we just talked about, which is the how the concentrations will change. So here you have a chart. It says initial equilibrium concentration of N2O4 and NO2 at 100 degrees Celsius. And I wrote the reaction here in red because that's not written in the table. So you might want to write that somewhere on the slide so that you know that this is the reaction that's it's corresponding to. And basically that was the same reaction that we just looked in with those two plots. So in this table, you have 4 experiments, and on each experiment, they tell you the initial amount of the reactant, NO2, and the product, N2O4, and then they give you the equilibrium concentration. So let's start with experiment 1. In experiment 1, you start off with 0.02 moles of molar reactants, but 0 molar, that means that there was no products present. And then once the reaction establishes equilibrium, the concentrations of NO2 and N2O4 are listed here and here respectively. For experiment 2 and 3, it's kind of the same thing, but notice that the initial amounts of NO2 are different. So all of these experiments, the concentrations of N2O4, the product is 0, and you're given initial amounts of reactants here, but they're a little different. So let's see, are the equilibrium values going to be the same? No, they won't. So here are the equilibrium concentrations. Because you're starting with different amounts of NO2, when it establishes equilibrium, you'll have different amounts of N2O4 and NO2 as well. And then finally, the last one, experiment 4, is a little different because in that case, you're not starting with the reactant, you're starting with the product. So basically, you're doing the reverse reaction. So for this reverse reaction, you have 0.02 molar N2O4, and then no reactants, of course. And again, equilibrium is established. And then you have different concentrations. Now, one thing you may notice is that experiment 3 and 4 both have the same amount equilibrium concentrations for N2O4 and NO2, and that's because they're basically you're starting with the same sort of amounts. And where am I getting this information from? I'm getting this information from, there is one typo here, and I want you to go ahead and correct that, which I'm going to do on mine. Sorry about that. So let's go ahead and just change that to 0.04 molar. That makes much more sense. Okay, so after you make the correction, let's come back here and we'll see that the equilibrium concentrations are the same. So you may be asking, well, why is that? Notice that the ratio of NO2 and N2O4 is a 2-to-1 ratio. So that means you should have double the amount of NO2 and that you have of N2O4. So if you have 0.02 molar N2O4, you should have 0.04 molar NO2. Right, just based on the ratio. So basically, you're starting off with the same amounts of thing. They're molar equivalents of each other. And so in that case, whether you're starting from the forward reaction or from the reverse reaction, you're going to have equilibrium concentrations. All right, so that's it for part 1. We're going to go on to part 2, where we actually start calculating some numbers.